Okay, we're going to continue with this example of a person at the pole versus a person at the equator. And I'm going to start with the person at the pole, and I'm going to sketch the forces that are acting on them at the pole. And here it's really the most simple case we looked at originally when we even started talking about forces, where you have a normal force that's pointed upward and the force of gravity that's pulling the person downward. And those are really the only two forces that are existing for this person. And there is zero acceleration for this person because they're not moving in a circular path, being at the pole while the Earth's spinning. So in this case, the normal force is equal to the weight of the person. And this is pretty much as we normally or usually expect for a person standing on a planet. We always have ignored the rotation of the Earth. Now let's consider somebody standing at the equator. If we apply Newton's second law in this case, unlike the case at the pole, at the equator we have a downward acceleration because there's a centripetal force that the person at the equator is going to experience because they are moving in a big circle at a speed v that we calculated a few videos ago to be about 465 meters per second. And the r, of course, is the radius of the Earth, so we'll have to calculate what the centripetal acceleration will be if we take 465 meters per second squared and divide it by the Earth's radius, which is 6,400,000 meters approximately. So now this difference between the normal force and the force due to gravity, which is equal to 0 at the poles, happens to be equal to this small negative number here. It would be negative the mass of the person times v squared over r. And I continue with that over here. And once we put in the numbers in this equation, of course, make Fg be equal to the person's mass times gravity. And this mv squared over r is the person's mass times v squared over r. What we'll find is that if we plug in v here and r, as I mentioned a few minutes ago, and then g over here, we'll see that the person's apparent weight is going to be slightly lower at the equator because of this term here. This term is going to subtract a small amount from this number mg right here. Kind of interesting that at the equator, on a perfectly spherical planet, a person would appear to weigh a little bit less because their normal force would be a little bit different. It would have this added term in it. It wouldn't just be their weight. That amount turns out to be 0.034. So the mass, I just factored that out. So we're only looking at the quantity v squared divided by r, where v is the 465 meters per second, and r is the radius of the Earth. If you subtract that from g, you will get what that person's apparent weight would be at the equator, and you'll see it'll be a tiny bit less. It's about 3% less at the equator than at the pole. And this results actually in, this is actually part of the reason why the Earth, it is the reason, the Earth has a slight bulge at the equator that you might have heard about. And this percentage is approximately the percentage of that bulge. As a result of the Earth rotating, its equator is slightly bulged outward. You might hear some discussion that that could be considered a centrifugal force. That results, a centrifugal would be an outward force. The centrifugal force is not one we talk about in this class or that we use. We just talk about the centripetal force. The centrifugal force is actually kind of like the Coriolis force. It's not a real force per se. It's something that we can use to explain certain things, but we can use the centripetal force to explain the same things. So in this case, we're using the centripetal force, and that gives us this result here, telling us that at the equator, a person will appear to weigh slightly less, and so will the crust of the Earth, which is why the crust of the Earth bulges outwards slightly at the equator as compared to the poles. And I want to conclude this discussion by imagining, let's say you're on a space station, and or even a big spaceship that's trying to get from Earth to Mars, or just living in space for some period of time. It's difficult to live in a zero gravity situation or a free fall situation, as we'll talk about soon. And it would be great if there were a way that we could actually experience something like gravity. And one proposed method for doing this is to have a spaceship that actually spins, rotates, where people live along the floor in fashion something like this. So this person's standing at this point in the floor, this person's standing at that point in the floor. As a result of the spinning of the space station, the person is going to experience a normal force that their feet will experience because this ship is rotating. There's no gravity that we're going to be considering here. It's literally just because of the spinning of this space station that they appear to experience, or they would experience something like gravity if the space station were turning fast enough. It would appear to them that if they dropped an object, because the space station is turning, the object would actually appear to fall because it would be touching something that's over here as that thing rotated to here. So it would have to spin relatively quickly for this to happen. But this is one way that gravity can be simulated in a space station using concepts of centripetal force. Okay, I'm going to end this lecture here, and we'll continue talking about the lab and centripetal force in the next video.